Okay, so good evening, ladies and gentlemen. This is Rabun Redar, the chairman of the SPA Northern Iraq section. It's a pleasure to be moderating our monthly speaker webinar for this month under the title Fundamentals of Nuclear Magnetic Resonance, NMR, in Petrophysics. A brief recap on our section. The SPA Northern Iraq section is a part of the Society of Petroleum Engineers, dedicated to advancing technical knowledge and professional development in the oil and gas industry. We connect professionals, students, and energy experts across the region through events, trainings, and knowledge sharing. It is our pleasure to welcome Professor Mohammed Mahmood from King Fahd University of Petroleum and Minerals as tonight's distinguished speaker. Thank you very much for your time, Doctor, and we really appreciate having you with us. So, Dr. Mohammed offers a variety of courses to students and industry professionals across the region, and they are honored by SPE and KFUPM for academic and professional excellence. They have been recognized as a leading researcher in environmentally friendly stimulation fluids for acidizing, acid fracturing, and hydraulic fracturing. They focus on enhancing productivity in both conventional and unconventional reservoirs. They have been awarded from KFUPM, the American Chemical Society, and the Society of Petrophysics and Well Log Analysts. They currently serve as an editor for AJSE and ACS Omega journals, and they are a member of the editorial advisory board for the Energy and Fuels Journal and Unconventional Resources Journal. Welcome again, everyone, and we wish you an insightful and informative session. And the mic is yours, Professor.
Okay, thank you for the introduction. Okay, so good evening, everyone. So today I'll be talking about the some like shed lights on the fundamentals of the nuclear magnetic resonance and petrophysics application in petroleum engineering. Actually, if you look at our title for the word like nuclear magnetic, we deal with resonance that is actually generated when we magnetize the nuclear atom, that we can get some useful information and properties from it. The properties that we call a spin and how it is related and also and how it relaxes and generates and forms the NMR signal. And the types of oscillation in NMR we have one and for example, NMR tool is not available and in the lab, so this can be modeled by also having some other properties measured in the lab, so we can simulate NMR signals as well, and some future directions for the NMR. So for the history of NMR, we have actually this field started with a very low magnetic field, which is 0.1 Tesla, and I think here all is the Nobel Prize holders for NMR research in general, not only in oil and gas fields. So in 1936, Gorter got the first Nobel Prize due to the discovery of paramagnetic relaxation. Rabi in 1945 also assessed the magnetic behavior of the nucleus. This actually, at this year, the basics and fundamentals of the NMR physics has started. In 1946, Bloch and Purcell, they discovered what we call as the Larmor frequency, at which the magnetic field is related to the frequency of the atom. In 1968, Ernst got also the having increased from 0.1 to 125 Tesla. So having increased in the magnetic field, this will widen the application of the NMR.
Pardon me, Dr. Mohammed. Are you changing the slides?
In different fields. In 1930, also, these two scientists with the Woodrich in 2002 introduced the interpretation of NMR frequency also at very high magnetic field at 10 Tesla, which we call it the biological NMR.
Dr.
So
Mohammed,
these are the
sorry
yes.
for the interruption. Are you changing the slides? Because the slides do not change from our side. Can you please stop sharing and then share your entire screen?
Okay.
Yes. Yes. Yes, it's perfect now. Thank you.
Okay. Clear now?
Yes, clear now.
Okay. So basically here I'm listing different, applications for NMR and with the Nobel Prize holders in, for different magnetic fields. They said, from 0.1 to 10 Tesla. So to have an NMR, this is what we call the Larmor frequency, which is actually related to the magnetic field and the gyromagnetic ratio. This is a property of the nucleus. So any nucleus that has this property, a value, larger value of this one, it will be sensitive to the NMR. It will have NMR response. In addition, also, we have what we call it a spin. Spin is a property of the nucleus, which actually describes the unpaired neutrons. In this case, we have, for example, the hydrogen. It's a spin number. We have it half. The hydrogen 2, it's 1. The carbon 12, 0. Carbon 13, for example, it has a spin property of half. The spin is actually, it could be half, 1, 1.5, 2, 2.5, and so on. So it's like we start from a spin number of half, for each nucleus. So all of these atoms that has the spin number, half and higher, it will be NMR sensitive, and we can actually detect it, for example. So like water has the hydrogen, also the gas and oil. So we can, this is why we use NMR in, for example, an oil and gas application, because we can count how much hydrogen due to its properties, the spin number. We cannot actually assess carbon 12 because its spin is 0, but carbon 13, which is the isotope for the carbon 12, we can detect it from NMR. In addition, also to the isotope O17 for the oxygen, and also the sodium 23, it has high spin number. In addition to the spin number, also the nucleus should have this what we call it the gyromagnetic ratio and the abundance in the nature. So if you look at the hydrogen, it has the highest gyromagnetic ratio and also the highest abundance among all, almost compared to the carbon 13 is very high as well. So we have to satisfy the 3 parameters. The nucleus should have a spin number, and it should have a gyromagnetic ratio, which actually this is the response of the nucleus to the magnetic field. And also it should, be existing in the nature and has natural abundance very high. So this is the ideal nuclei for NMR response. Also, the magnetic field affects the application and measurements in oil and gas. Yes.
We can't see the slides changing. Can you share your entire screen while you start sharing on Google Meet?
Okay, so can you see now?
Yes, it's now changed. It would be better if you do not start the presentation, just present it like that.
Okay, okay, sure.
Yeah, because you've started showing your presentation file and not the presentation. That's why. Yeah, now better. Yeah, thank you.
Okay, okay. So in addition to the again the spin numbers and the general magnetic ratio and the natural abundance, we have the magnetic field also affects the application of the NMR. For example, in the lab and field for the NMR application in oil and gas, we are talking about very small magnetic field. You know, it's like 40 microtesla, 50 microtesla, even or 0.1 Tesla. This for the logging tool application, and also for the core analysis, we have wide range in the lab. It can reach up to 3 Tesla. This in the lab. So for the clinical diagnostics, we have to get imaging, we have to have a very high magnetic field and also very high frequency. So each tool has its own magnetic field and also frequency. Both will determine the resolution, the application, and the properties that we can get. So the MRI, we don't have so far downhole MRI tool, but we have it in the lab, magnetic resonance imaging, which is very similar to the clinical applications. The ones that currently we have in the field is the low magnetic field and also low frequency, which is the around 2 megahertz. For the higher the magnetic field, this will give us the NMR spectroscopy. This is actually for the molecular structure applications in chemistry and solid state physics. So we have 3 application. Oil and gas application starts with low magnetic field and low frequency. Intermediate application, which is the medical clinical industry. And in the high field and very high frequency, this is actually the molecular structure. If you have specific chemicals and would like to investigate the chemical structure, how many carbon, hydrogen, and the structure of this chemical, we should go for the high magnetic field and high frequency NMR. So the relaxation, actually what we have a magnetic field. We apply external magnetic field. So for example, these are the protons that existing in the fluid. It has a specific direction, which is the hydrogen nucleus. And then we apply a magnetic field, which is, this is B0 in this direction. So all the nuclei actually will align with this magnetic field. And then we apply another magnetic field, which is perpendicular to this one. And again, the nuclei will align with the applied magnetic field. And then we release this magnetic field B1 to B0 again. So this is what will happen. The random, these actual nuclei will go back to their original, direction. It depends. For example, if one in this direction, it will go to the right direction. And if one in the left direction, like this one going through this direction, it will go to the left hand side direction. So in the NMR tool, we have, we apply the source, what we call it the radio frequency. And then we have like the receivers also that counts the nuclei relaxation and spin. So for we have 2 types of the relaxation. And again, I have like some animation here, but I'm not sure if it will show. Anyhow, so the first type, or the first relaxation time, we call it spin lattice. This is basically happens across the Z direction. So if we have the nuclei aligned in this direction, what is the time it will take to reach to demagnetize? Because if you look at this, when we apply the B1, the nucleus will have full magnetization. And when we release this magnetic field, it will go back to the original magnetic field. It will take some time in both XY direction and Z direction. So the time it will take to relax back to the original magnetic field in the Z direction, we call it T1, the relaxation time T1, which is longitudinal. And the one that it will take in the XY direction, we call it the T2. And then we do what we call it an inversion recovery process for this NMR. This is the signal, the original, the signal versus, the time. So this is what we record, and until it reaches actually the thermal full equilibrium, and this is will lose its full magnetization. So also the T2 time, as I said, it is in the XY direction. So how long it will take for this to dephase? So for example, we give 90 degrees and then we release, and then 180 degrees. So this is the process of measurement of the magnetic field. So we change the direction of the magnetic field to study the property of the spin and how it will behave in the XYZ direction. In T2 here, we are looking for the defacing only in the XY direction, or what we call it defacing. So if you look at this animation, originally the NMR, it will be again in this direction, then we will flip it to the, if you look at the animation, yes, now it is in the vertical direction, 90 degrees, it will deface in XY, then we will flip it 180. So also and measure the defacing, and then we give it what we call is the echo time. So after a specific time, we repeat this process by by hitting the magnetic field in 90-degree direction, and then 180-degree direction, and then this what we repeat, what we call it the echo spin, which is this time here in this equation, to get some like how signal that we can measure and interpret. For example, if you look at this equation, we have this is the T2, what we call it, and this basically what we get from the logging tool, the T time, the T2 time relaxation. It is a function of different parameters. We will explain later. Okay, then we fit actually what we have. This is the, if you look at the previous one, this data, we fit it to specific models. One of these models, we have what we call it CPMG, and actually the terminology CPMG, this is the letter from the 4 scientists. So we have 4 scientists here. This is the initial letter from each one of them who actually has came up with this, process of inversion. So once we fed this data to a specific model, this is the experimental data and this is the model fitting. We do this process of the fitting the data, we call it regularization. And this one, we can actually do our own regularization, or we can rely on the manufacturer of the NMR tool inversion algorithm. This basically is a very simple code. So we can invert, for example, this equation and to get what we call is the distribution, of the pore system inside the formation. So this is the frequency here, and this is the time of the relaxation. So for example, here we have like different peaks. We can say 1, 2, 3 peaks. This indicates how many pore systems that we have in the rock sample. And again, this rock system should be sensitive to the magnetic field, in which it should have hydrogen protons, like water or oil or gas. So the elements of the relaxation time, the T2 decay, again, the T2, we said it is the time it will take for the spin to dephase in the XY direction from a B1 magnetic field to a B0 magnetic field. This is the time it will take to relax. So this is the apparent relaxation time, and it actually consists of 3 sub-relaxation times. The first one, we call it bulk relaxation time, surface relaxation time, and the diffusion relaxation time. So weak relaxation, it means longer T2, and strong or fast relaxation, short T2. So the components of the T2, first, we are talking about the T2 bulk. This is basically the effect of the solution viscosity, because we are talking about how the proton of the hydrogen will spin in the bulk of the solutions that we have. So the viscosity will have a big effect here, and also somehow the density and the temperature, as we can see. So from this T2 bulk, we can have some information about the viscosity of the fluid. This is why NMR we can use if you have a bulk solution, for example, in a bottle, and you expose it to the NMR measurements, what we will get is what we call a T2 bulk. Okay, because there is no rock sample in the solution, only we are talking about fluid. So this will give us information about the viscosity. So for example, for water, the T2 bulk is like 3 to 4. For gas, it is 1 to 5. For oil, it could be very, very small to very high. So it depends on, the viscosity of the fluid and the pressure as well and temperature. So in medium and heavy oil, the bulk relaxation will be dominant. And for water and light hydrocarbons, the bulk relaxation is minor. This is why, for example, if you look at as we said, the components T2 bulk, T2 surface, and T2 diffusion. So if this one is dominant in this equation, the other two parameters will not contribute a lot to this one. So, and if, for example, this one is minor, the other two parameters will be the dominant one. So this is actually, in each application, we can see which one is dominant, which one is minor, and what is the information that we can get from this equation. So for the second one, the surface relaxation, which is the most important one in the T2 relaxation. Surface, it means the rock surface. So basically, this what the time it takes for the nuclei to actually relax at the surface of the rock. So this will be a strong function of the pore geometry or the pore characteristics, which is related to the porosity. So this is a function of what we call it the surface relaxivity, this term rho, and also to the S over V ratio. S over V ratio, which is the surface area to the volume ratio of the pore itself. S over V actually is 1 over R. This is the radius of the pore, because the surface area of the pore itself related to the radius, and also this is the R square, and the volume will be R, which, like if you consider it a sphere, this will be R to the power 3. To R square divided by R to the power 3, this will give us 1 over R. So we can remove S over V and put 1 over R. And this ρ2, which is the surface relaxivity, this is a property for each rock. For example, for calcite, it is 5 or 3. For sandstone, we have a value for clay and so on. So we have this parameter, which is a constant value, and this is what we get from the NMR. Then we can get the R, which is the pore size. So this one very important application for the NMR, in which we can get the pore size distribution of the rock sample. We can get small pore size, medium, and larger pore size. So we can convert the T2 relaxation to pore size distribution, and this is very important in various applications. For example, one very simple application is the gravel packing, and also the, for example, the drilling fluid design. If you are going to design the weighting material for drilling fluid, we add what we call it fine medium calcium carbonate solids to again prevent the filtration of the drilling fluid and build the filter cake to prevent the formation damage. And all of this information, we get it from the NMR, T2 surface. And the last one, which what we call it the diffusion, and this is the equation for diffusion. It is actually function of what we call it the diffusion coefficient, or the diffusivity. The diffusion, actually, what does it mean, diffusion here? We apply magnetic field, and this magnetic field usually is homogeneous. But if you have in the rock itself what we call it paramagnetic or diamagnetic ions, like, for example, manganese, iron-rich minerals, and so on, this will impact the magnetic field and will create what we call it magnetic field gradient. So this magnetic field gradient will impact the relaxation, and we have what we call it diffusion. So this term which should be considered. But we can neglect this diffusion if we don't have these paramagnetic or diamagnetic ions, and we have only the magnetic fields that we apply, and the Earth magnetic field is very small compared to the ones that we apply. So in this case, we can neglect the effect in this equation, and we can, just consider the other two. So back to this equation again. So we have T2 bulk, and this we said that if you have a very viscous fluid, This one will be dominant, which is not the case in most of the reservoir. We could have water, oil, and gas. This one, we have, if we have inhomogeneity of the magnetic field, what we call it magnetic field gradient, usually we don't have the case. So usually the dominant one is the surface relaxation, which is related to the pore size distribution. So this is why we can take the T2 response as only 1 over T2S and neglect the other two parameters. Again, this in most of the cases, I would say 90% of the cases. In very, very specific cases, like if you have organic material, you have bitumen, you have asphaltene, you have heavy oil, we cannot neglect this part and we have to consider. In iron-rich minerals, which paramagnetic fields are there, so also we cannot neglect this one, we have to consider. But I'm talking about the popular cases that we have. Also for, again, back to this, the T1, this is how we measure it. We actually have what we call it the wait time. We apply magnetic field and wait for example, specific time, and then we apply this magnetic field and then wait and apply until we reach a full equilibrium to get this equation. So if you look at this equation, it has no diffusion. It's only bulk relaxation and surface relaxation. So the diffusion part, if you have any magnetic field inhomogeneity, does not affect the T1 because it's in the in the Z direction or the longitudinal direction. It doesn't have to the spin lattice, which is related to the mineral itself. So, but why we don't use T1? T1, it takes longer time to get this full recovery compared to the T2. T2, we can get it in a very shorter time compared to the T1. This is why the logging application, we use T2 just because to save time and to save the cost of the job. So this is the summary for the relaxation time T1 and T2 and the components for both. For example, if you look at the fluids here, an impact on the T1, T2 in water from 1 to 3. So the in gas, for example, T1 is much greater than T2. In oil, T1 is almost equals to T2. So generally, we look at for T2 because in most of the reservoir we drill with water-based mud, and the depth of investigation of the measurement of the NMR tool, we are talking about on average 4 inches, which basically in the invaded zone. In the invaded zone, we usually have water-based drilling fluids. So this is why we use T2 again to get the information in shorter times. Okay, so again, as I said, we usually go with the assumption that the T2 has no effect and the T2 diffusion, because this is only for viscous fluids. And this one, when we have magnetic field inhomogeneity, which is not the case in most of the applications, so we cancel both. And if we have rock saturated with 100% water, the only impacting, component of the T2 will be the surface relaxation time. And this actually example reflects the surface relaxation. So if you have, a proton that spins and to relax to the surface, so this is the rock sample, and this is the water. So this will be basically only the T2 surface, which is affecting the relaxation, how long it will take to reach to the surface and relax. And this is related to the pore size. So this is why from the T2 directly we can get the pore size and porosity. So if you look at the different minerals, for example, for clay, silt, fine, and coarse grains or pores. So the smaller the pore size, the shorter the relaxation time. So the larger the relaxation time, the bigger the pore size. And this is the surface relaxivity parameter, which is the unit in micrometer per second. For example, for sandstone, it is 5, for clay, it is 1. So once we get the T2 and we know this information based on the mineralogy, we can get the pore size distribution. So we can get the pore size distribution and also the porosity. At 0 time, the relaxation of the NMR gives us the total porosity. So NMR, we call it is lithology independent tool. So I don't care about the lithology because it doesn't matter, because to get the porosity, not the pore size. The pore size, if you would like to get this distribution, which is how many smaller pores, medium pores, and larger pores, and what is the contribution of each pore system to the total porosity. For example, we have 30 here. Larger pores contribute with 15%, the medium pore contribute with 10%, and the smaller pores contribute with 5%. To get this detailed information, we should know the lithology. But to get the total porosity, which is basically, this is the intercept here at 0 time for the full exponential decay curve. This will give us the porosity, which is 10%. We don't have to know the lithology. But to get this information, the inversion recovery or the pore size itself, this is time. If you'd like to convert this time to micrometer, we should know the lithology, because we have to have this parameter, surface relaxivity. So how to actually, this is the fitting for this equation, is exponential equation, multi-exponents. So what we can do, for example, just fit this one, which is the smaller pores. This one here is the larger pores, and this one is the intermediate pores. So we can have, for example, we call it micro, meso, and macro pore systems. So this is what we call a triple porosity system. Again, this is the advantage of the NMR. You can know the breakdown of your pore system in the reservoir, not like other logging tool, for example, neutron and density and sonic tools. You just get an information about the bulk and total porosity. But NMR, you will get the distribution, the pore size distribution, the component. This is very important in different application and designing, for example, enhanced flow recovery fluids, and also for like to improve the sweep efficiency. Where does your fluid exist? I mean, if you have micro pore, macro pore, do we have this pore, for example, only filled with water, or we have some oil and gas that we can produce? So this is the final outcomes that we get from the NMR, even in the lab or the field. And then we fit this. It depends on the how many fitting. It could be only one, for example, larger pore. It could be 2, it could be 3. Again, based on this fitting. For example, this is the fit of the larger pores. So if you just put this equation, and if we, for example, move this curve here, it will fit only the larger pore system. And then if you put the other curve, it will, for example, only fit the intermediate section here. And the latest one, it can fit only, for example, the smaller pores, which is in this section here. So again, this is also what we can get from the NMR. The volumetric distribution of the fluid. This is the total signal, and then after this, after we do inversion, for example, using the exponential fitting, and from this also we can determine how much hydrocarbon, how much mobile water, how much capillary bound water, how much clay bound water, or even dry clay. So all of these components we can get it from the NMR by having what we call it T2 cutoff. So, for example, this parameters or the cutoff values, we can get it from the lab by running a centrifuge experiment, and to know where is the free water, for example, and get an NMR scan. So we know this is the T2 cutoff, and then you can do another, for example, spinning for the sample to remove the capillary water, and also we can get a specific cutoff. So these cutoffs are not constant for, it depends on the rock type. We can get it in the lab, and then we can apply it in the field as well. So in the field, what will be the outcomes for the NMR? You can get the hydrocarbon saturation, you can get the free water saturation, and you can get the bound water saturation, which is very important to avoid the free water saturation production. Again, no other tool can give us this information except in the NMR. Other tools give you just the water saturation without the identification if you are going to produce the whole amount of water, or just this water. It could have capillary and mobile water. Again, this is an example of how to determine the pore size. For a sphere, for example, we can have S over V, which is basically 1 over R. Again, this is an approximation. It could be 3 over 4. Again, because the volume of the sphere, and this is the surface area, for example, so for a sphere as well. And it depends on the mineralogy that you have. Look at the sandstone, for example, surface relaxivity 23, and for dolomite 5, for limestone 3. So, for example, for a sandstone, the pore size for 100, for a T2 relaxation of 33 millisecond, it will be 0.759 micrometer. Again, this for sandstone. For calcite, it will be completely different. It will be, smaller than this one, because of the surface relaxivity is almost 1/5 compared to the sandstone. This is why converting NMR to pore size distribution, we should know the mineralogy again to get these parameters in the equation. NMR is a very reliable tool if we compare the core porosity to the NMR porosity from the lab measurements. So we have a very good fit within 1% one porosity unit. All the data fits very well. So we can rely on NMR to give us, correct estimation for the porosity. So for the NMR in petrophysics, as I said, the NMR, we can get the first parameter is the porosity. For example, here, this is the impact or the effect of the frequency on the porosity. At low frequency, 1 megahertz, for example, we have a very good fit between the lab porosity and the NMR porosity. Having higher magnetic field, for example, like 85, we have deviation. At 2 megahertz, also we have a very good fit. Again, this tells us, what the frequency of the tool itself, it will impact the porosity determination. So this is why the lab tool and field tool is 2 megahertz and less. In addition, also we can get the viscosity of the oil from what we call the bulk measurement. So if you just have a tube filled with the fluid, oil or water, for example, here we have the brine and different oils, and in this equation, the only dominant part will be the bulk, because we don't have rock. There is no, restrictions for the fluids, the H hydrogen proton to move and relax. It's only in the bulk solution. So look at the, for example, the brine, it has the largest relaxation because the viscosity, if the viscosity is 1. So look at this one, the larger the viscosity, for example, this will shift to the left, For example, oil 1, which is a viscosity 41, so this one. Oil 2 is very similar to this one. Oil 4, which is basically this one, very viscous, it goes to the left. So the relaxation is a function of viscosity. The higher the viscosity, the lower the relaxation time. So we can get from this, the viscosity of the fluid from the NMR. Brine or water is just single component, so will give us normal distribution. Most of the oils, they have like the oil, different components, heavier component, light component, intermediate component. So you will get different peaks. This will represent the heavier component of the oil. This will be the lighter component of the oil and so on. But for water, it's only one component. This is why we have normal distribution. So again, this is what we can get from the NMR. In addition to porosity, we can get the viscosity. We can get also the pore size distribution. This is the rock sample. We can decompose the relaxation, the bulk relaxation, for example, or the overall relaxation signal to different ones, for example, smaller, intermediate, and larger one to get exactly the pore size distribution of the rock sample. Okay. So also, as I mentioned before, the diffusion term, which is this one, this can happen due to what we call the magnetic field inhomogeneity, which we have magnetic field gradient. Like, for example, this figure here shows that the magnetic field, it has a gradient and different localized different location. It means the solid itself, it contributes to the magnetic field. So we could have iron, manganese, for example, some clay minerals, also like nickel, usually found in clay minerals. This like considered as paramagnetic ions, elements, and this will impact the magnetic field. So in this case, we cannot consider we have homogeneous magnetic field, and this term will be considered and also affect the measurements. Also, we can get permeability. We have two common correlations just from the T2 time, the T2 log mean, just to take the log mean, for example, of the NMR response and plug in this equation, in addition to the porosity, which is the area under the curve. Or also we have some correlations that depends on what we call it the bound fluid index or the bulk fluid index, and also the free fluid index and bound volume index, which is this one, for example, the free, and this is the bound, and just apply this in the equation of specific parameters so we can get the permeability. Also, wettability. NMR can give us, an information about the rock wettability by having different measurements. For example, the bulk fluid measurements and the saturated rock measurements. So, for example, this is the bulk for the water, and this is the water in the rock. So, for example, if this shift happens, it means, for example, if no shift at all happens, like this one, this is bulk oil and oil in the rock, it means the fluid is, for example, like water wet. And if you have this one, for example, like this case, could be oil wet. So we have developed some like quantitative assessment, for wettability estimation from NMR. In summary, NMR can be used to really quantify the rock wettability much better even than like other like contact angle, and also maybe some other lab measurements. Clay also, it will impact the performance of the NMR. For example, here we have rocks with different clay content. So for example, the higher the clay content, so look, this one affects the NMR response. And from this, for example, we can, by just having the T2 number itself, we can see how much clay do we have in the NMR, in the formation. Also, we can get the clay distribution, like, for example, kaolinite, light. NMR is very sensitive to clay minerals, and so we can get this from NMR. Again, here back to the wettability evaluation. For example, these are different rocks. At the end here, we have what we call it the NMR wettability index. This basically, you need to have just water wettability index, oil wettability index. You need to get the bulk water, which is the bottle of water, and the bottle of oil, and measure this one. And the rock itself saturated as the residual oil saturation, and the rock saturated at connate water saturation. Just these measures. So we have to have like 4 measurements: bulk oil, bulk water, residual oil saturation, T2, the core itself, and the core sample saturated with connate water saturation, and substitute in this equation, and this will give us the NMR wettability index. And this is like fairly match with the, for example, these ones, the circles, fairly match with the lab measurement of the wettability index. And this is a very quick. The lab ones, it can take, for example, very long time to measure. In the NMR, it doesn't take like few hours to get this index. In addition, also, NMR simulation can be done. If you look at the T2 equation, we just need the surface relaxivity and the pore size distribution. Pore size distribution, we can get it from the micro CT, for example, and the surface relaxivity also, if you know the mineral, we know the value, and then we can do simulation, and then you can match it with the experimental. So you can get the NMR simulation response if we don't have, like NMR facility as well. So also the NMR can be used to determine the bound fluid, which includes, this is the chemically bound water, the clay bound water, the capillary bound water. So all of this water, which we call it immobile water, that we cannot produce from the formation, and this will help us in assessing the saturation. For example, like this one, the clay bound water and the bound volume as well. So all of this water, it is important to see in your formation if you have a mobile water or free water. So again, this will help design the surface facilities, and also design, the production strategies, the perforation, where to perforate to avoid, for example, high mobile water saturations in some formations. So having this from the NMR will help a lot to, again, get good production from oil and gas fields. Also, as mentioned before, NMR can be used to determine the permeability from these two correlations. And here we have some examples of the NMR measured data in the lab. And this is the NMR estimated permeability from the previous two correlations. It has some good match, with some of the correlations. So, overall, NMR is a good tool also that can be used to estimate the permeability. For example, here in low permeability, it doesn't work well. In high permeability, it works. So again, we need, when we're using NMR, we should be cautious that it doesn't always work to give us good permeability estimation. This is another permeability correlation as well. So again, we have different correlations that can be used. Also, another application in petrophysics, we can use it for fluid typing. So we can get, for example, the different fluids by having the T1 relaxation time, T2 relaxation time, and diffusivity, which is the diffusion of the fluid. This is what we call it, the multi-dimensional NMR. So the single dimension means like I'm just using a single measurement, either T1, T2 diffusion. The multi-dimensional NMR, we integrate two different measurements. It could be T1, T2, it could be T2 diffusion or T1 diffusion. So this is what we call it, the multi-dimensional NMR. From this, we can get what we call it the fluid typing, and we can differentiate between, for example, if you have oil, water, heavy oil, or for example, different fluids. So the mobile water or the water in general will have different response for example, T1, T2, and diffusion. So by combining two parameters, T2 and diffusion, for example, you can easily distinguish between oil and water, because, for example, the diffusion in oil is very slow, and for example, in water is medium. So easy you can, if you just combine the T2, we can get actually very good differentiation between hydrocarbon, mobile oil, or even if you have gas as well. This for the fluid type. So this one shows that the NMR porosity in the field, in actual carbonate field, it matches fairly well with the core data, the core porosity with NMR. This is the neutron density porosity as well. We have some differences between the core. So again, this is because of 5% clay in this section. NMR was much better compared to the neutron density porosity in this one. So again, NMR can be considered as a very reliable tool for porosity estimation. In addition, we can get the bound and free fluids, for example. So you can come at a specific section. This is you can say like, yeah, this is the bound fluid that we cannot produce, and this is the lighter color, the lighter one, which is the free water, and this is the red one is the oil. So you can avoid, for example, perforating in the free water sections to avoid water production, and just target the this bound water, because bound water will not be produced. All you are going to produce oil from this section. So again, this is the field application or the well logging application of having this fluid typing method by this differentiation between oil, water, bound oil, water, movable or free water. Again, NMR is the one of the best tools that can give us this in the field, and we can use it to estimate the free water. Again, this table shows in general the fluid type, and the knowledge of the fluid type in the reservoir is essential actually for both lab and field measurements. And this is how to differentiate between these by integrating different parameters like diffusion, T1 and T2. For example, the water, it will have almost this correlation like T1 1.5 times the T2. In the oil, T1 equal T2. But when it comes to the diffusion, also we can differentiate between oil and water easily. And also for the gas, usually the diffusion is the major parameters that we use to define, and also because T1 is much greater than T2. So overall, we have these measurements in NMR, T1, T2, and diffusion that we take it from the lab measurements to the field measurements. And in this case, we can have a very good, formation evaluation or assessment for our reservoir to get this really nice distribution by estimating the permeability, NMR porosity, and also the saturations. So you don't have to have like resistivity tools, or whatever, like to determine water saturation. So only from one tool, you can get porosity, oil saturation, water saturation, not only water saturation, also the breakdown of the water saturation, the bound and the free water saturation from the NMR tool. So, yeah, by is it? I almost finished what I have, and thank you very much. If you have any question or comments, we'll be glad to answer.
Thank you very much, Professor Mohammed, for this insightful and informative session. It was a true privilege to have you with us this evening. So before we bring the session to a close, I would like to open the floor for any questions. So if you have something to ask, just please feel free to unmute or just drop your question in the chat box.
Thank you, Dr. Mohammed, for such a presentation. It was really a good one. and I think you covered it all. But I had a question regarding NMR porosity readings and core porosity. I mean, what is what is the difference between these two readings in this?
Yes, sorry,
Thank you
Moed.
so much, Dr. Mohammed, for taking the time to be with us and sharing your knowledge and expertise. We are, as an SPE, really appreciate the efforts you put into making this session happen. And it's mean a lot to all of us in here. And thank you for your efforts.
Yeah, welcome. Thank you. My pleasure. So your question was about the difference between core porosity and NMR porosity, right?
Actually, it's not my question, it's Badr Khan's question.
Yeah, okay. So for the core porosity, this is actually the helium porosity that we measure in the lab with the helium porometer, or also with the saturation method, which is a very simple, straightforward one. For the NMR, again, you just saturate the core with the water, and we put it and get this, if you remember this figure, which is the fitting of the signal, and to get the total porosity at 0 time, which is the intercept, of the fitting with the y-axis at 0 time. So this is the NMR porosity. Sometimes you could have difference. NMR is the total porosity, but the one we measured in the lab is the effective or the interconnected porosity, So if we have any mind, usually the core samples that we have is, the porosity, it has almost all effective. This is why it matches very well. So this is why you'll have a big difference if you have clays. So clay porosity will be different in the labs than the NMR. NMR will give a higher porosity for the clays compared to the the lab, because the lab will not consider clay porosity, but the NMR can also give us the porosity in the clay itself. So it will be overestimating. This is why NMR is deficient if we have like clays, and also it is deficient if we have heavy oil. And I'm not sure if you know about this, what we call it geosteering, in directional drilling and horizontal drilling. So basically, geosteering is used to, maximize the contact between the drilled well and the oil producing sections. And in case they have, for example, shale sections, if they have like very heavy oil sections that they cannot be produced, they use NMR in addition to the neutron density porosity. Neutron density porosity is very effective in shale and in heavy oil. It will give us a very correct porosity. NMR will not. So they use this difference, which is the NMR deficient in this case, to deviate again away from these sections that will be non-productive. So overall, NMR, if it has like clay, it will not be accurate, and if we have heavy oil, it will not be accurate as well. But in the most of the cases, the conventional cases, yes, NMR is a very good effective tool for porosity estimation.
Thank you, Kakto, for your answer and for your time and sharing your experience with us. Thank you so much.
Yeah,
It's all clear now.
Harman says, what was the most surprising or counterintuitive insight you've personally discovered during your years of working with NMR in petrophysics?
Yes, actually, we have started working in NMR almost like 15 years ago, and we were surprised that NMR, it can almost do, I was expecting like, for example, 1-2 parameters, but NMR can do more than 20 specific and single measurements. Everything you imagine, we can do it with NMR. But again, this in the lab. In the field, we have some restrictions because of the size of the tool, the frequency. In the lab, we can go to frequency, for example, 125 megahertz. We can go like 3 Tesla in terms of magnetic field. In the field, no, we are limited with 2 megahertz and 0.1 Tesla. In addition, for example, we can detect sodium in the lab. We cannot do it in the field. So this can give us salinity of the water. Again, this can eliminate the use of other logs for salinity estimation. And also we have, for example, this is diffusion that I talked about. We have, several applications in diffusion, like the anisotropy. If you are talking about, for example, the completion, the direction of the perforation, where to direct your perforation, which side. If you have a vertical well, you have an XY direction, we have what we call it permeability anisotropy in the horizontal section itself, I'm not talking about the horizontal permeability. The horizontal permeability has 2 components, for example, right? Tx and Ty. And which direction to perforate, X or Y? The only tool that can give us is the NMR. So again, you can maximize the production by knowing the highest permeability direction in the XY direction itself, which we call it. If you look at the Darcy equation, we have KH. This KH is both KX and KY, the components. So if you get a mean, to know because of the in situ stresses, are different, sigma X and sigma Y, you have big contrast between both. This will impact permeability. In addition, also will impact the production. NMR also, we good to know that it can give us this information.
Thank you, Professor. As someone working on drilling fluids, I'm curious. So, do you see potential for NMR techniques to be applied in monitoring filtrate invasion or the performance of fluid loss additives in real time?
Yes, NMR actually is being used as a real-time tool during drilling. And yes, for the invasion, yes, again, this for only water-based drilling fluid. For oil, it might cause some issues because we realize that we have water in the embedded zone. Yes, you can assess, for example, the filtration, and even this can help you better design your drilling fluid to what we call it maybe damage, if you have filtration damage, if you have interaction between the drilling fluid and the formation itself. NMR can assess the formation damage due to drilling fluid as well. Yeah, it can be used.
Oh, thank you. Abdul Ghani says, what advice would you give to young researchers or engineers trying to interpret NMR log data in early career field projects with limited access to lab support?
Yeah, actually, NMR, understanding the physics of NMR is very important. So I would advise you to go with the very basic fundamentals, understanding what does the T1 means, T2 diffusion, the terms. And we have some very specific parameters, that actually we use, like the wait time, the echo time. What are these parameters? How actually the surface companies have set these parameters? Which regularization method they have used? Because it depends. For example, in your fitting, you can fit the equation with multi-modal system or just unimodal system. So again, having lab support is very important as well, because the lab, we can visualize the rock sample and look at the NMR response in the field, and this will give us some confidence about the algorithms that we have used for fitting. So I would say lab is a very essential component for interpreting the NMR data, and also this cutoff, how to define the bound water, the free water, and the oil, for example. These cutoff values, we get it from the lab. We cannot just assume it hypothetically, because it differs from rock to rock, from reservoir to reservoir. It's not like universal or constant values.
Thank you once again, Professor, for your enlightening session. Again, on behalf of the SPA Northern Iraq section, we really appreciate your time and the valuable insights you shared. And to our attendees, thank you very much for being with us. And we hope to see you again at our future webinars. Have a wonderful evening, everyone.
Thank you. See you. Thank you.